We'll run through these really rapidly in the sense that everything I just wrote on the piece of paper is typed onto this slide, okay? So you have it in 2 spots. So our definition is there in blue. Enthalpy is equal to heat transfer during an isobaric process, that's key. And here's our basic equation. I can, if I want to properly write this out in a differential form, I have dH would be equal to du plus pdV plus vdP if I take the derivative with respect to both volume and pressure. But we said we only care about this for constant pressure, so that last term, just throw it away. I probably won't ever write it again. We don't need it. And enthalpy is really relevant for us because most biological reactions are happening under constant pressure. We are considering, again, the human body is isothermal, isobaric. Are we also isovolumetric? Yeah, for the most part. Another way to think about that, and I think it's written on the next slide, liquid and solids, kind of incompressible. We're not going to think about this the way ideal gases are going to compress and expand, okay? It'll be negligible volume change. So here's our simplified equation, and then we can plug in work for this piece here, depending on if we're talking about pressure volume work. And this again goes through the steps I just went through. So you have them on the slides as well. Most biological processes are at atmospheric pressure. For human body, we're going to use by body temp always, or I'll ask you to use standard temp 298 K. And we're going to have negligible change in volume, such that this, actually both of these drop out. And an enthalpy change is approximately an internal energy change. Okay. Write it this way, which means our internal energy change is approximately heat flow. Okay. This is easy to measure. The reason we want this is because all of the experimentation we're going to talk about going forward, calorimetry, is all built on capturing changes in heat flowing in and out of our calorimeter, okay? Temperature and heat are the things we can measure. Actually measuring when the bond is breaking and all the bond rearrangements of enthalpy, not easy. Total heat change, easy to capture experimentally. Okay. So the reason we want this, we can measure changes in heat. That's when it's useful to us. So again, enthalpy approximates the internal energy of a system when you can say we're both at constant pressure and constant volume. Okay? Won't be applicable in every case. You got to read what rules I put into the problem prompt, but for the human body, it is actually relevant. This is valuable to us because heat's a lot easier to measure than this other stuff. One example would be if I have a protein and it's going to bind to a ligand, or a ligand. What is an example of a ligand or a ligand that you know of? Hemoglobin's the protein. What does it bind? Oxygen, okay? So my ligand could be the oxygen binding to the hemoglobin. It's typically this format is I'm the bigger molecule and I am some small molecule binding to it. So it's, you know, protein binding to a drug or a transcription factor binding to the DNA strand or whatever. Those are kind of both large. When these two things bind and form a complex, what do you expect the change in heat to be? What happens when these two things come together and form non-covalent interactions? Is that favorable? Yes. Will energy come out? What sign is that? Yeah, I'm making new interactions. I'm expecting heat to come out of my instrument when this happens.